Okay, in this presentation we are going to look at the distribution of continuous random variables. So just to begin with, we have a definition of the cumulative distribution function f, capital F, of a random variable x, and that is denoted capital F of x as opposed to small f of x, and that is the probability that x will be less than or equal to some value of x. Again, that's small x. So capital X is the name of the variable, small x is some possible value of x, okay? And f of x is the probability that x will be less than or equal to this particular value of x, this possible value of x, okay? So x is some real number, capital X is the name of the variable. Now, for all of the examples, what we're going to do is assume that there's some function small f of x such that f of x equals the integral from minus infinity to x, which is this value here, of this function f of t dt. Okay? When you evaluate this definite integral out, what you'll get is an expression in terms of x. So we sort of use a different variable name when we are creating this integral expression here, just so when you get out an answer, it's in terms of x because of the upper limit being x. Now this is for all real number x, all real numbers of x, okay? Now small f is known as the probability density function of x. So there is a relationship between capital F of x and small f of x, okay? And again, just to highlight that it's a convention to actually write this variable, this expression here, in terms of a variable other than x. So that's why we use t there. But what happens is when you evaluate it out as a definite integral, it becomes an expression in x. Okay, so just watch out for that. So here we have some of the properties of the probability density function small f of the continuous random variable x. Okay, so f of x is greater than or equal to 0 for all values of x. Now, for regions of interest, usually it's the positive values, but if it's non-negative, that's good, but it can't be negative, okay? So it can take the value 0 in certain regions. We won't be particularly interested in them, but it's mathematically plausible and viable. Now, between the upper and lower limits of integration, usually denoted in the maximum case minus infinity to infinity, the density function, when we integrate that with respect to dx, that is equal to 1. Okay, and also if we want to get an interval, the probability of an interval of values, a is between x is between a and b, what we can do there is evaluate that definite integral where a is the lower limit, b is the upper limit, and get the definite integral of f of x dx for all a and b. Okay, now probabilities correspond to areas under the curve f of x. Okay, so for any single value a, the probability of x equal to a is negligible, so tiny that we consider that equal to 0. Okay, so that's the exact value. Now, sorry, just to clarify, x is a continuous random variable in this case, and this does not apply to discrete random variables. So essentially what we have here is a couple of expressions that we can treat as being equal to each other. So just actually notice that we have different operators. We have less than and less than or equal to. Okay. By the same token, we can actually switch them around and use greater than and greater than or equal to. But essentially all of these four expressions are equal to each other. So the probability of x being less than b but greater than a is equal to the probability of x being greater than or equal to a but less than b. Okay, and so on. So essentially what we have here is four possible combinations of greater than and greater than or equal to. But as far as we are concerned with regards to continuous random variables, these are all equal to each other. Okay, that's a very important thing for continuous random variables. Now anyway, let's look at an example. Let x denote the width in millimeters of metal pipes in an automated production line. If x has the following probability density function, calculate the following probabilities. Here, f of x equals 10 times e to the minus 10 times x minus 5.5, where x is greater than or equal to 5.5. Otherwise, if x is less than or equal to 5.5 or less than 5.5, the probability density function is 0. So this is the key part here. 10 times e to the minus 10 times x to the minus 5.5. Okay? Now what we're asked to do here is calculate the probability of x less than 5.7, greater than 6, and between 5.6 and 6. So essentially what we're going to do is 3 definite integrals using the probability density function. Now, this is the sort of thing that you're going to come across quite a lot when you're dealing with probability density functions and doing calculus on them. You will be expected to be very quick with the integrals related to the exponential function. Okay, so this stuff is considered bread and butter. Now, I essentially put down a whole load of identities here, with particular emphasis on the one we're about to use. This one, the second one, would be particularly important. The integral of e to the ax dx is equal to 1 over a times e to the ax plus k. Okay, so essentially what we're doing here is whatever the constant is in the power, when we evaluate the integral, essentially 1 over a, whatever that is, whatever that constant is, just divide by the constant. Okay, so this is one we are going to use in particular for this presentation, but just in general, if you're doing any sort of work with probability density functions, all of this needs to be, you need to be going straight out the gate with it. You need to be, you can almost state them verbatim, like as shown. You don't have to sort of prove anything, but you really need to know all of these off by heart and be ready to go with them very quickly. Okay, so just watch out for that. This one also is very useful in some cases. So this is the first part of the question. Calculate the probability of x being less than 5.7. Well, just as a quick remark, the probability of x being less than 5.5 is 0. Okay, so we can just sort of remark upon that just to start with. That means our definite integral is a definite integral between 5.5 and 5.7. Basically, the integral between 0 and 5.5 will just automatically evaluate to 0. Okay, so we can just disregard that and look at this particular range of values, 5.5 to 5.7. The probability density function is 10 times e to the minus 10 times x minus 5.5 dx. Okay, so here we have e to the ax. Here a is equal to minus 10. Okay, and just using that identity I discussed previously, when we evaluate this integral out, we get 1 over a times e to the ax. And that's our definite integral. So that means what we have there is 10 divided by minus 10. So we end up with minus e to the power of minus 10 times x minus 5.5. Okay, so this is our expression here. What we do is evaluate it at the upper and lower limits. Okay, so what we do when we get evaluated at 5.5, so let's just look at the lower limit first. X minus 5.5. 5.5 minus 5.5 is 0. So minus e to the power of 0 is 1. Okay, so so that, just watch out for that. When we evaluated minus 5.7, we got 10 times x minus 5.5. So 0.2 times 10 is 2. E to the minus 2. Okay, so essentially what we'll work out as, what we evaluated conventionally, we get this. Okay, so that's 5.7 there. And that's 5.5. Just rearrange it algebraically. What we get there is 1 minus e to the minus 2. Bit of calculator work, that is 0.865. Great. So part B, something similar. Probability of x greater than or equal to 6. This is the integral from 6 to infinity. So essentially what we do is, same thing again, we just have different limits of integration. So e to the minus infinity is considered to be 0. So what we're left with here is minus e to the minus 10 times 0.5. So that 10 times 0.5 is 5. So what we're left with is 0 minus e to the minus 5. Bit of calculator work. Essentially that turns into e to the minus 5. And that becomes 0.007. Okay. And last one again, what we have here is, essentially we can go straight here because it's essentially just different limits of integration each time. So working this out, what we get here is, when we evaluate it at 6, we get 0. We get e to the minus 5. Okay, evaluate at 6, we get minus e to the minus 5. When we evaluate at 5.6, we get minus e to the minus 10 times 0.1, which is e to the minus 1. So going in the correct order, what we get is this. Okay, rearranging it algebraically, we just sort of simplify it out. We get e to the minus 1 minus e to the minus 5. It's essentially this expression just tidied up. Bit of calculator work, and we get 0.361. So that's it. That is using probability density functions.